I'm indeed very honored to be able to present this Ørsted Lecture, and I couldn't agree more with him, the words that you heard of his perception of what science and technology needs to do for society. I have had a wonderful hospitality and had a chance to visit several departments here at the university as well as at the RISO campus, and I'm very impressed by the activities that are going on here. So what I would plan to do is to talk mainly about climate change, but let me first put it in perspective. Again, going back to the role of science and technology, it's clear that the progress of civilization, particularly in this the last century and continuing with this one, it has been very spectacular. So many advances that we have. For example, the life expectancy has more than doubled just in the last 50 years alone. Okay. So there's no doubt that there are lots of improvements, but there are some problems as well, and that has to do with the fact that there are many of us here in this planet, and we have limited natural resources. And taking this picture from the cover of this magazine, The Economist, I'm taking this from my colleague, Paul Crutzen. It's his idea with whom that I shared the Nobel Prize in '95. He suggested that we no longer live in the Holocene. You know, these last 10,000 years, the climate and conditions in our planet have been very steady. That's what made possible civilization to really progress as we have it now. But it turns out that the main force now to change what's happening on the surface of the planet is no longer natural forces, it has to do with human activities. In fact, for example, a bit more than half of the land surface of the planet has been changed by human activities. Okay? And so this fact that we have limited natural resources means that we have to use them wisely. Sustainability is the key word there, in a way that they allow future generations to continue with this progress that we have enjoyed ourselves, and even our own generation, of course. Limited natural resources, some of that is obvious. All of you know about, for example, fisheries in the oceans. The major fisheries, many of them are actually being depleted. However, there are examples in some places where the fisherman society, industry has gotten together and are doing that sustainably in a way that you only take as much fish out as can be replenished by nature. Unfortunately, that's not happening all over the planet, but it certainly can be done. But there's another place where we have a limited natural resource. So let me just show you this picture of our planet, and that's the Earth's atmosphere. Because the atmosphere is very thin, it's like the skin of an apple, relatively speaking, more or less in that proportion where most of the mass of the atmosphere is concentrated 10 to 50 kilometers above the Earth's surface. There's atmosphere all the way up to many kilometers, but it becomes very, very thin and doesn't affect our activities that much. Okay, well, what's limited is not the atmosphere itself, of course, but it's its capacity to take care, to absorb the wastes from human activities without having consequences that might be a problem for the progress of society. So that's the situation in terms of the atmosphere. But there's one more interesting factor, which, again, well known, relatively simple, which is that because of the winds and the way the atmosphere functions, if you have some emissions, say here in Denmark, or of some compounds or some gases that remain at least several months in the atmosphere, then they get mixed in that time scale throughout the northern hemisphere. And it takes about a year and a half to mix in the southern hemisphere as well. So this means that if you emit compounds, gases, particles, but mainly gases, that remain several years in the atmosphere, then you have truly a global problem, because it doesn't matter anymore where they were emitted. They just mix throughout the planet. We have just a few examples of that. One is stratospheric ozone depletion, what I was involved with some years ago, but I will not be talking about that. I'll be talking about climate, just as one example of I want to emphasize and to put it in context of the problem that society faces today. It's perhaps the largest and most serious environmental problem that society has ever faced. But there are other problems with limited resources in terms of biodiversity, availability of water, and so on and so forth, air quality. So some of those are connected with climate, but I will focus my talk just on climate change as one problem that we have, that asking the question, what's happening and can we do something about it? So first on the science, I know some of you are experts on climate issues, climate change, science, or technology, but nevertheless, what I'm going to do is to be very general and assume that not all of you are scientists, and so I would just repeat that briefly. And here's what's happening. What we're worried about is the thermal balance of the planet, and it's whether we are affecting that or not. So in this picture, what we have is just a representation of how this thermal balance works, namely, our planet gets energy from the sun, mostly in the form of visible radiation, and we know that for millions of years already, this thermal balance, or we could call it steady state or quasi-equilibrium, is at work, namely that the planet loses about the same amount of energy as it receives. It's practically the same. There's a little bit of internal energy inside the planet, occasionally lost through volcanoes, but it's a minor factor in this balance. So the greenhouse effect has to do with the fact that the atmosphere affects in some way this thermal balance. I'm going to come back to this graph in a moment, but first I want to sort of review the basic science. And don't worry, if you're not a scientist, I'm not going to dwell on the equations in great detail, but they have great historical significance. First of all, what's in the graph is just the wavelength depends on the type of radiation that we're talking about, visible light from the sun, but the planet loses the same amount of radiation, but in the infrared. But the basic equation that describes how this happens is due to Plancks Distribution Law, which Planck developed early in last century. And that's a very important equation. Planck received a Nobel Prize for that, by the way. And the question that was asked at that time is sort of black body radiation, any object in the laboratory or our planet loses energy just because it's at a certain temperature. And it's obvious to all of us, if you increase the temperature until you get like a heater, if it gets red hot, it loses a lot more energy. Or an incandescent bulb is white hot, so it loses even more energy, okay? But our planet is fortunately not red hot, but it loses energy in the infrared, okay? And Planck just attempted to describe the measurements. And he came up with this remarkable, what looks relatively simple equation. And the only way to interpret what was happening in the laboratory was to come up with quantum mechanics, namely that energy comes in packets. So it's just remarkable that such a fundamental law that has so much impact on what we do today. I want to turn this off just in case, but it's more just to show you this is one example. These TV, anything, cars. so much of what we do today with electronics is sort of based on the fact that quantum mechanics is work. We understand how nature works at the molecular level. And by the way, Einstein, who would also receive the Nobel Prize, but not for relativity, it was actually for the photoelectric effect. It's sort of the same idea, except instead of just saying energy comes in packets, the energy in radiation, light also comes in packets that we know we call photons. And the energy of those photons depends on the wavelength. Okay. And Boltzmann is also important. Boltzmann did not receive the Nobel Prize, but that's because he was born too early. Okay. It was, the Nobel Prize came about later. But just something interesting about Boltzmann, he had problems towards the end of his life. That was towards the very end of the 19th century and the beginning of the 20th century, because at that time there was a controversy that he had to deal with. It was whether molecules actually exist. Okay. There was the question whether matter was continuous or not. So imagine that's only a little over a century ago. It's not that long ago. And just a few years later, these sort of laws. But I wanted to put that in perspective because the contribution that Ørsted makes is fantastic. Okay, just associating magnetism with electricity is at the basis of electromagnetism. And of course, Maxwell later quantifying that with the equations. But that's basic science that we depend so much on. And that's basic science, very well established for climate. Okay. So anyhow, that's just a little bit of history. But coming back here to what's happening to our planet, you can measure how much energy comes from the sun. You can notice that about a third gets reflected by clouds and by snow and so on. And then you can use Planck's equation and calculate what should be the average surface temperature of the planet. And the answer is minus 18 degrees Celsius. Something is wrong. If that was right, we wouldn't be here. The oceans would be frozen. Life would not have evolved. But it's not Planck. Okay? It's just that the planet's a little bit more complicated. That is, in fact, the temperature at which the Earth emits on the average, but it's not at the surface. It's somewhere higher up in the atmosphere. Why? Because it turns out that our atmosphere has some trace gases, mostly carbon dioxide, water vapor, and a few others, that absorb some of this infrared radiation that is emitted by the surface. Let me just recap. Those 2/3 of the energy that come from the sun get to the surface. So what is warmed up by the sun is the Earth's surface. So the surface emits this energy, but part of that energy is absorbed not by nitrogen and oxygen. If the atmosphere were to be that clean, we would still be at minus 18. But because of those trace gases, it functions as a blanket, and so it ends up that the average surface temperature is plus 15, not minus 18. So the 33 degrees difference is what we call the natural greenhouse effect. And that's really not in question, okay? That's well established. That's how the planet sort of functions. There's a lot more to it, and there's physical chemistry and so on, and climatology can do the details, but I won't bore you with the details anymore. But let me talk now about the gases themselves. Carbon dioxide being the main greenhouse gas. And what we have here, what we call the pulse of the planet. How does carbon dioxide change with the seasons in our planet? It goes up and down. And we have there the northern hemisphere with the stronger oscillations up here, and then the southern hemisphere, it's actually out of phase 6 months, going up and down. Why? Because carbon dioxide is biologically active. We breathe oxygen, and some of that oxygen, when we exhale, becomes carbon dioxide. Why? Because fortunately we can use the chemical energy. The oxygen that we breathe oxidizes food like hydrocarbons, carbon and hydrogen, so you get CO2 and water vapor as a product, and we can walk, move, eat, and so on with that energy, okay? And so that's why carbon dioxide sort of increases at some seasons, mostly you can see it going up and down summer and winter, but fortunately something else happens. If not, we would no longer have oxygen in the planet if we were only using it up, and you know what it is. It's, of course, photosynthesis. So green plants do exactly the opposite. They take carbon dioxide from the air, but they need energy in this case, which is the sun, solar energy, plus carbon dioxide plus water vapor. And it's just the same thing, but in reverse. They make, among other things, carbohydrates, food. And we eat the carbohydrates, or we eat animals that eat the carbohydrates. Okay. So we get the food back, and that's hence the oscillations, winter and summer, which are 6 months out of phase in the southern hemisphere. So that's all the natural atmosphere. And these were the first historical, very clean measurements of these gases by my colleague, David Keeling. He actually died a few years ago, but at Scripps institution, which is part of the University of California at San Diego. So you can see the northern, southern hemisphere. Why, by the way, more oscillations in the northern hemisphere? That's relatively simple to explain. That's just the topology of our planet. Most of the continental mass is in the north. So the southern hemisphere has less land, less photosynthesis. Okay, but, wow, something else happening. It's going up. It's not because we're breathing more or breathing less, okay? We're burning fossil fuels, okay? So photosynthesis created organic matter over millions of years, and in just decades, we're burning that and putting that back in the atmosphere. So that's why it's changing that fast, okay? So what I'm going to do next is to answer in a very brief way without too much science, but just a question, since this is an important greenhouse gas that affects, obviously, the functioning of the thermal functioning of the planet, does it matter? And what I'll do is I'll summarize the results as done by this panel, the IPCC, Intergovernmental Panel on Climate Change, which is just a group of voluntary scientists from many countries, of course, many Danish ones, and a few from Mexico, like myself. A few thousand, but really just a few hundred are the ones that did most of the work, okay? And what they did, what this group does is every 4 or 5 years publishes a report. They don't do research, just evaluating what is happening with climate from the perspective of evaluating the scientific literature. And so I'll just give you the results. And the results I'll condense in again, this group does not do research, but they examine the literature. It's clear from the literature, we know that already. This is another version of David Keeling's measurements, but he didn't do this anymore. This was over a 10,000-year period. And you can see how it suddenly goes up. That's when the Industrial Revolution starts, okay? When we start burning fossil fuels. Coal, as well as oil, petroleum, gasoline, diesel, and so on. So it just suddenly jumps, and it's now about 40% more than it used to be for a long, long time, okay? Thousands of years, so actually a couple of million years. If we have time, we'll go back to that. But there's another gas, which is methane. That's the main constituent of natural gas. Wow, it also jumps. Where does the methane come from? We actually, we use it, as you know, we burn it and we can generate energy by burning it. But why did it jump? Well, it turns out that the main production of methane, there's one way to get methane, it's out of the ground, it comes together with oil, but that's not the major source. Major source is biological. It's bacterial activity, okay? It's anaerobic. Bacteria make methane. That means in the absence of oxygen, when bacteria digest organic material, food. And those are the conditions that you have in the digestive system of ruminants, cattle. So that's the increase in human population goes together with the increase in cattle. There's another source, which is rice paddies, because they are flooded, no oxygen, source of methane. So it also jumps, okay. Fine, so this is just one set of measurements examined by the IPCC. This is another set of measurements, temperature. It's not trivial to measure the surface temperature of the planet, but recently you can do it with thermometers. It's again not trivial because many measurements were not done very carefully, but there's a very clear consensus that temperatures jumped, and if you go back 1,000 years, there are no thermometers, so you have to infer that, for example, from the width of tree rings or coral reefs or sediments in the oceans or in lakes and so on. And so you can get different interpretations. But there is little doubt now, it's very well established that there's a jump in temperature just in the last century. Not very much, it's less than 1 degree, it's about 0.7, 0.8 degrees Celsius. The question that the IPCC then, this panel asks, are these two measurements connected? And the conclusion is yes. This temperature increase is a consequence of the change in the chemical composition of the atmosphere because there are greenhouse gases and so on and so forth. But, and part of that, we're not really sure. Why? Because the Earth is a very complex system, just like our bodies, our brain, and so on. So we have to do statistics. Because it's possible that this is a fluke, that this occurs naturally, but it's not very likely. The consensus of the IPCC is that there's a 90% probability, 90, okay, that this temperature change is a consequence of human activities. But we're humble, there are uncertainties that you have to deal with. One more piece of information, water vapor is a stronger absorber than carbon dioxide. It absorbs roughly 3/4 of the radiation emitted by the surface. So you could say, well, if carbon dioxide changes, it doesn't matter that much. But water vapor, the amount of water vapor in the atmosphere is actually controlled by CO2 and by the other gases because it has to do with the hydrological cycle. There is an unlimited amount of water in the planet as far as how much to put in the atmosphere from the oceans and so on, but it has to do with temperature. But water evaporates and condenses. So if you do a simple experiment, you cannot do it realistically, of course, you do it in the computer, but you remove CO2 from the atmosphere and the non-condensable gases and see what happens to the water vapor, it begins to condense. And in a few decades, you would reach this minus 18 degrees that I was mentioning. If you remove the greenhouse gases, remove water vapor, then you go back to Planck's equation, very cold. Okay. Actually, it gets a little cooler because the planet, there's a lot of snow and it reflects a larger fraction of incoming radiation. Okay, so here it just wanted to give you hints that the science is actually rather well established. Okay. The science of climate change, and but there are uncertainties. Issues like the role of clouds, the role of atmospheric particles. It's difficult to project, but you can actually do measurements and put limits on that. But let me move next to, so what? It doesn't look like a big temperature change, 0.8 degrees Celsius, but things are happening. Glaciers are melting, not all of them, but most of them. Sea level is rising. It's only about 20 centimeters now since the Industrial Revolution. It's not very much, but the worry is what more can happen. But perhaps the biggest worry is what we call extreme weather events. Okay. Floods, they're increasing just everywhere. Forest fires, not too far from here, if you turn on the TV, there are some big forest fires in the United States now, in Colorado, and last year in California, and so on. There are always forest fires, but we're worried about, again, this increasing frequency. So there's a question that the scientific community is raising, and only very recently beginning to tackle it in a consistent way, which is, are these extreme weather events, so does have to do anything with climate change? Is it caused by human activities? Okay. And so in this forum last year, many scientists were still very reluctant to make a connection, but it's becoming now fairly clear. For example, my colleagues in Potsdam in Germany, they've made a much clearer analysis, and they do conclude that certainly the heat waves as one type of extremes, but also precipitation extremes. I understand even here in Copenhagen you had some unusual rains, okay? So if it's only here, who knows, but it's happening in so many places that it's, to say the least, suspicious. But what this analysis does then is, again, try to put probabilities, and the probability is now very significant according to the scientific analysis. But there are still some skeptics in the scientific community for this. But the way this is done, I just put here the analysis of another colleague, Kevin Trember. It depends how you ask the question. So some scientists are the ones that are doubting that are asking the question, would this flood or this extreme weather event, would it have occurred without human activities? That's the wrong question. Maybe in the future we will see some of those events. The insight is the following, that those events would have occurred anyhow, they're natural. But they are occurring with more intensity, and that's a different question. Okay? The intensity of the extremes is what is changing, and it's very obvious if you look at it from the perspective of heat waves. Here we have measurements. This is no longer speculation, do you think this is this or that? We have here measurements in different years of temperature distributions, and it's just like a Gaussian. Okay? Some places are much warmer than others, and if you shift the temperature only 0.8 degrees, you're shifting these curves. And if you look, you define what is a heat wave, an extremely hot summer, and if you look at it as 3 sigma, those of you that look at the normal distributions as 3 standard deviations, well, you can just see that the probability has increased about 40 times. If you do this quantitatively, wow, it's no longer negligible. It's 40 times more likely in certain places to have what is called a heat wave if you define it as a 3 standard deviation departure from the norm. Okay? And so that means that it's very likely that this type of anomalies had to do with that. Of course, in Europe, you had this large heat wave in 2003, and you could probably begin to do the same type of analysis. So why is this important? I'll come back to this because this means the bottom line for these extreme weather events, which I hope I'll have time to come back to, is that we are no longer just worried about what's going to happen at the end of the century. Okay, one misconception about climate change is, we're worrying about if we continue emissions, by the end of the century, then we'll have some possible consequences that will maybe my grandchildren or great-great-grandchildren will have to worry about. No, we already have to worry about ourselves about these things. Okay, so I'm going to change place back here, okay? And why? Because now I'm asking another question. What can society do about this, and what is likely that society will do about this? And there is an international process convened by the United Nations, the Framework Convention, to see whether you can reach some sort of international negotiation. So, there was this important one here in Copenhagen in the middle of the winter. Actually, it was pretty cold. But what was interesting about this particular meeting is that there were many heads of state, more than 120, I think 130 and so on. I was able to come. I came with President Calderon from Mexico. And what was remarkable is that there was no objection from any head of state to this sort of aspirational goal, we could call it. Let's try to see whether we can manage to change the way society functions so that the temperature doesn't increase more than 2 degrees. And why 2? Part of the answer, I'll give it a moment, has to do with science. And part of it has to do with economics, because if you want to change society very fast, it turns out that's very expensive. But the fact that has to do with science has to do with risk, okay? That if you increase it more than 2 degrees, you begin to worry about certain things happening. Okay, but not much happened. Unfortunately, this was just wishful thinking. There was no formal agreement, and there have been 2 more meetings in Cancun and then in Durban, and there's still no formal agreement, the main bottleneck being internal politics in the United States, which I hope I'll have time to get into a little bit in a few moments. But let's first see what would it take to limit this temperature increase to 2 degrees. First of all, another reason for 2, this is just a rough indication of what might happen if the temperature increases by 2, 3, 4, or 5. And this is just to mention that there are a few things that would be positive. Longer growing seasons in some northern countries, okay? But even there, if you increase the temperature too much, even there it begins to be a problem. And so most things that happen, at least from this perspective, have negative consequences for the economy and for the functioning of society. And we have here extreme weather events, and we have the possibility of these irreversible impacts, which again I hope I'll mention in a moment. But before that, just can we do that? Is it possible to limit the temperature increase to 2 degrees? Well, first you'll analyze where are these emissions coming from. The red is fossil fuels, the main reason for CO2 increase, but the other reason is green here, and that's photosynthesis. If you remove tropical forests or if you change the land, you decrease the capacity of the planet to convert CO2 back to oxygen, okay? So you have to deal with all of these issues. And the bottom line, I'll show you a couple of graphs, but this is the first one, is that if we measure emissions from burning fossil fuels and from deforestation and so on, we are on the red line at the moment. This is very, very long term. But if you want the temperature not to go above 2 degrees, you have to reduce emissions very dramatically so that you remain on the yellow line. Okay. In a little bit more detail, but just in the next few decades, you already have to cut emissions. If you look, that's part of the same graph. This is emissions. This is historical, but this is where we are going now. They keep increasing because the economy keeps advancing, both in the developed as well as in the developing world. And so historically, we're on the way up. But you have to cut them by half, or it depends relative to what year you measure it, but this is a very large change in the way society functions, okay? Just use half the energy, or how do you do this? These huge cuts in emissions, okay? Are they terribly expensive? Well, here is what experts conceive as the solution. The bottom line is very positive. Yes, it can be done. It's actually feasible. And it's done in this concept is that these stabilization triangles is one way to look at it. But the point is that the solution means you have to do many things simultaneously. There's no so-called silver bullet, like, let's use nuclear energy and we solve the problem. No. You have to do lots of things. Some of them are, and the first ones here have to do with using energy much more efficiently than we have done it in the past. And it can be done because energy has been so cheap so far, just pulling oil off the ground, that there was really no need to be very efficient. But the potential is very, very large to improve there. And of course, using renewable energies instead of fossil fuels, forest management, biofuels, all sorts of things. So let me give you a few examples of this. Wind. particularly here in Denmark. Of course, you are leaders in terms of developing these windmills, and Denmark just made a commitment to double the fraction of the energy that comes out of wind. So that's one way to not to use fossil fuels. And there's a limit, of course, because it's intermittent and it has to be coupled to other sources of energy. But solar is yet another one. Germany, for example, uses quite a bit of solar energy. I'll say a few words about Mexico, but in Mexico we barely use solar energy, and we have a lot more sun than Germany, okay? So we have a lot of potential, but here these are just some pictures of, in Seville, of what's called solar thermal energy. The other way to do it is with photovoltaic panels, converting just directly solar photons into electrical energy. And until recently, these photovoltaic panels were considerably more expensive, but the price is coming down fast, and China wants to get be the most important exporter. And so they're making already solar panels on such a massive scale that they are beginning to compete with solar thermal, and in fact, with fossil fuels as well. It's still more expensive, but they're trying to get there. Of course, this is not everybody's happy about that. In the United States, the claim is it's what's called dumping, that they artificially lower the price so that they get the market, and then they can profit from that. But the United States is also making solar panels, and Spain, and so on. So anyhow, these are examples of renewable energies that do not depend on fossil fuels. Oh, we could spend a full hour talking about nuclear, but we won't have time. But you know, your neighbors here in Germany and Japan decided not to use nuclear energy anymore. That's a very drastic step. That's because Fukushima, the accidents in Japan. But the other side of the coin, if you want, is that the accident happened with very obsolete nuclear plants. They were about to be closed down. So what the consensus is among some of my colleagues, I tend to agree with them, is that nuclear should be one option, at least from the perspective of the not second, no longer, but third and fourth generation nuclear plants that are much safer. Okay, you can design it to be more safer. They're, of course, a bit more expensive. You can deal with the nuclear waste problem. It's very political, but it's possible. Perhaps the most worrisome problem with nuclear is proliferation. Countries like Iran or North Korea that use nuclear energy perhaps a bit as an excuse to have materials for nuclear weapons. Okay? But that's again politics, that's not really technology, and even that can perhaps be solved. So anyhow, nuclear is one option that does not emit CO2, and the one way in which you can continue using, for example, coal. You know, the United States and China, their main source of electricity is from burning coal, which emits a lot of CO2. You could do that if you capture the CO2, separate it, and then store it on the ground. Surprisingly, there are enough cavities, so-called saline domes, to store huge amounts of CO2. But it's clearly much more expensive than just venting it to the atmosphere. Okay, so this turned out to be more expensive than originally anticipated, and so there are some years delay in actually applying this technology. Norway just opened a big plant to show that whether this can work or not. You know, they have a lot of oil as well. And in Mexico, we have a project, but it's more for a pilot plant for capacity building, when instead of just burning the CO2, it's going to be used to extract more petroleum in depleted oil wells. Okay, so you put CO2, you pressurize with CO2. Mexico pressurized years ago with nitrogen, but they were not aware of climate change 2 decades ago. So they made huge nitrogen plants. Anyhow, so this is a glimpse of what the solutions would be. Okay, energy efficiency and different forms of energy. But the bottom line there is that until the technology advances enough so that these new forms of energy are cheaper than fossil fuels, that might take a while. It's too risky to wait for that, although we're trying very hard, okay? And Denmark is a very good example. You're making a lot of progress there, so that's why it is very important that you keep doing that, okay? But it's risky because it's getting close, but ideally there should be an international agreement that puts a price on emissions so that these other forms of energy compete much more favorably, okay? And of course, you need to put a lot more effort in technology development, international cooperation, and the win-win measures are these energy efficiency measures that countries like Mexico are pushing that there. Since it's profitable, you should do that already because the economy improves with these win-win measures of energy efficiency, whereas things like carbon capture and storage cost, unless you increase the price, you won't get there, okay? So here is, in some sense, a summary of this perspective that I take from my colleagues at MIT. I was working with this group for many years. One way to communicate this to society or to policymakers, if you take this picture and put it together, it's as if though we're playing a game of roulette. And we are now on this roulette, okay, the one that has a lot of red, yellow, and so on. That's what we're doing now. Why roulette? Because we have uncertainties in our projections. Climate is complicated. So it's a gamble. If we're lucky, temperature would only increase 3, 4 degrees, but if we're unlucky, it could change more than 6 degrees. And it's all within the realm of current climate models because of the uncertainties in feedbacks and so on and so forth. And the MIT model is one of the 4 or 5 global models that is well accepted, and the others have very similar results, okay? But we can change roulette, and that's the point, of course. With these stabilization wedges, I should have called them, not triangles, namely doing renewable energy and so on. It's still a roulette because if we are unlucky, temperature would indeed go above 2 degrees, but it's a lot less likely, okay? By the way, 2 degrees now, it's very unlikely because we haven't started already. So we're talking more about an aspirational goal of 2.5 degrees, possibly 3. Okay, why a roulette? The other concept to explain to people in general is that in gambling, you gamble for money. So let's assume that I propose you to play a game that if the temperature doesn't go above, say, 3.5 degrees, and you have a choice of the roulettes, you earn $100,000. But you have this roulette here, okay? But then I offer you, I can change it, but you have to pay me something. Okay, but it's much more likely that you will gain. Okay, how much would you be willing to pay me if you have this $100,000 as what you might gain with the game, okay? And so how do you do this? Well, economists do this, okay? And particularly environmental economists, and this has been done by several groups. I won't poll you here, but many of my students were willing to say, well, since I'm bound to lose there, I'll pay $20,000, $30,000, something like that. It turns out it's only $1,000 or maybe $2,000, okay? So it's 1 or 2% of global GDP. Of course, I'm exaggerating a little bit because that's a lot of money. But it's still less, and that's a consensus among economists, it's clearly less than what you have to pay with these weather extremes. Floods, droughts are particularly expensive, and that's already happening, okay? It's not what you have to pay in the future, it's things you're already having to pay. And see, I have to run a little faster, but let me just mention that there are other more recent studies, not just for the planet, but here I just have an example for California, a recent economic study. What would they have to do to reduce emissions as much as is needed? Well, they have to massively electrify, change from fossil fuels to electricity that is generated with renewable energy. But the cost, again, it's for the, you know, California is the 6th largest world economy. And so they're talking about something of the order of 1%. Okay. In Mexico, by the way, where I have this center that I have, I won't have time to describe a lot, but one of our aims is to develop low carbon growth plans, economic growth plans, so that the government can think of alternatives to reduce emissions. And what we can already do in Mexico is these so-called win-win measures to remove subsidies that fund energy or gasoline when it's really not acceptable. But some of the other measures, it will require international collaboration. Okay, there is already a climate change law in Mexico that just passed. But to do the more expensive projects, you have to, it's qualified, there has to be an international agreement, otherwise, of course, Mexico would lose competitiveness. Anyhow, this could be done. But, whoops, well, I should remind you of the red part there. Why do we worry about that? Well, because it's possible. These are the causal tipping elements. It's conceivable, and there's some probability of the order of what we were saying there, 15, 10, 20%, that these things might begin to happen. The Arctic sea ice is already melting, but it's quite possible that the Amazon rainforest would actually completely disappear. Okay, that's an important lung for the planet, or that the boreal forest would also change, and so on. This, or the thermohaline circulation, that's the sort of thing that keeps the climate as you have it now here in Europe. You'll be pretty cold otherwise. So anyhow, these are things that are conceivable that could happen, and the point is to mention it in this context. From the point of view of economics, we're talking about risk. And even though I mentioned that it's already clear that it's cheaper to make these changes than to pay for the damage, there are some studies like Weizmann's at Harvard where he says, look, what should dominate our decisions are the risks like the red ones that I was pointing out there. It's not the most likely thing, but it has such enormous consequences that it doesn't make sense for society to take that risk, particularly because we can pay for it. I mean, it's something we can afford. And just to mention something from, I could have put a lot of quotes from DTU because you have done so much work, so I just have one that I almost choose at random. But in terms of risks, okay, society is very poor at understanding what's the risk, and that's one of the reasons that climate change has so much difficulties being accepted. But there are ways to treat risk in a very professional way. You can measure it, calculate it, and so on. And that's what this group here has done with prospect theory. You can quantify it. Clearly, you come up to the same conclusions. But the point is that society is actually not this sophisticated. It would be quite enough for us to convince politicians that the risk is too large and that they should reach an international agreement. Okay? So I'm very slow, so I'm going to move very fast now. I will skip this, but just to mention that chemistry plays a very important role, that we know what has happened to the climate in the last 500,000 years. These are ice ages that are triggered by changes in the parameters of the Earth's orbit, but CO2 plays a very important role. But chemistry is able to do that by looking at ice cores. You can count 500,000 years, okay, if you go to Greenland, which belongs to you here. So there are cores in Greenland and also in Antarctica, and you can count about 6, now almost 800,000 years back, and measure how much methane, how much CO2 you had at that time, and with isotopic analysis measure the temperature. But look where we are with CO2. Okay, we're well above the last 500,000 years, and I could go back several million years. And if we do nothing, we could double or triple it. And this has happened before. But there was no civilization then. And the planet was quite different. The continents were in a different part, but this is the so-called PETM, the Paleocene thermal maximum. And the temperature increased about 6-7 degrees at that time. And, but it happened in 20,000 years, okay? We worry that we're doing that in just 1 century or in decades. But the planet, with these changes, turned out to be different, okay? You had crocodiles in the North Pole, so it was a different planet. And it changed, it was a very dramatic change. So it's just an example of what science can do looking back. But briefly, I will just finish with this topic very briefly. Why is there so much misconception in the public about this? Scientists agree, most of them. There are a few, and we discussed with them, so we know why they have this position. But the vast majority of climate scientists agree that human activity is what's causing us the problems. But the media doesn't. Media likes to point out that there are two sides. The side that says climate is just changing naturally, and the other side is what scientists say, okay? Well, because of that, the public in the United States has this misconception, of course. I could argue that the same thing happens if you look at two sides of the coin. The same sort of situation should happen with astrology. Why? Because there are actually 12% of the US population that really dismisses climate change science. There are actually about 20% that believe in astrology. And yet the newspapers don't quite give you the astrological perspective on every political question. Okay? It's not very sort of fashionable, but for climate change it is, and the numbers are quite comparable. Okay? Anyhow, this is, in the US, why do I mention this? Because this is the main problem in the United States. I'll sort of mention this and then I basically finish. The main problem in the United States is the Republican Party has taken as a dogma not to accept climate change science, to think that's a hoax, that it's something that scientists are creating to get more money or something like that. But because of that, there's no chance that the United States would approve an international agreement today. We hope that with extreme weather events, with political climate changing, that things like astrology and creationism and so on will no longer be so powerful in the next few years, and maybe we'll get an international agreement, okay? But let me, see, I spent a lot of time, before I change, I just mentioned this, there was this recent article with some scientists claiming that we shouldn't worry about it. But these scientists are, only one of them is Dick Linson, I know very well because he was my neighbor at MIT, but what he has published we have discussed at length. We don't think he has any validity, and the others have absolutely no competence in climate. That's why my colleagues wrote back, if you want to learn about climate, ask climate scientists. You don't ask your dentist for if you have a heart attack. But should I ask my dentist if I have a heart attack? He would surely tell me, go and see your cardiologist. Okay? But that's not what the politicians in the US do. Anyhow, let me just see whether, yes, let me just finish with this graph. It's taking too much time. Populations also suddenly increased, okay? And it's jumped, and the problem is only about a fourth of this population is what has caused this change in the chemical composition of the planet. And the big challenge we have is the 3/4 that remain are the developing countries and so on. And people there, of course, also have a right to a better standard of living, to economic growth and so on. But what we have to do, it's not the way we have done it historically. So that's a big challenge we have and you have as young people here to make sure that economic development continues, but not the same way we've done it in the past. Obviously, there are two main reasons, and I stress the economic reason. It's clear that's cheaper. But I'll finish with the ethical reason, and that's our generation has a responsibility with the next generations not to leave a planet where there's a risk. We're not entirely sure, but where there's a risk that they will have a very difficult time increasing their standard of living, particularly for the very poor people in our planet. I think I better stop here. Thank you for your attention.